Welcome to lecture number 11. So now we are at the point where we can discuss semiconductor band diagrams. All along, so far we've been trying to figure out how to estimate energies, etc., and then also we've been looking at how to represent the k-axis in E-k diagram. Now that we have learned all that, and in the previous lecture I also gave a quick brief on how you could use these band diagrams to explain some of the things such as in aluminum, a negative Hall coefficient, etc. So and the notion of conductivity in context of band diagrams. So the things we've learned is how to plot E-k diagrams. We have learned some kind of information on the electron dynamics, what kind of information we can get from band diagram. In order to do so, we have defined that if we want to use equations such as force equal to mass times acceleration, then what kind of mass we can use. We have defined a quantity called effective mass. Having put together all these things in this first module, today we're going to start with the second part of the module, where now we're going to use all this information and start making sense out of them, use them, and show how this can be applied to devices, etc. So today I'll start showing you actual semiconductor band diagrams, and we'll try to interpret and try to get information out of them about those particular semiconductor materials such as silicon, gallium arsenide, gallium phosphide, germanium, etc. Okay, to begin with, let's start with semiconductors itself. So let's start with semiconductor materials. When we talk about semiconductor materials, let's name some such as silicon, the most common one, which is extensively used. And notice this course on optoelectronics, silicon is not one of the materials which is known for optoelectronic properties. It's not used in optoelectronics. So it's a good opportunity for us to learn why silicon cannot be used. Another important one is germanium, used sometimes in very specialized applications such as detectors. Why? That's a different issue, but again a material not used in optoelectronics. Another material, gallium arsenide, and its derivatives, several forms of it, gallium arsenide or gallium aluminum arsenide. When mixed up, these materials you have seen in optoelectronics. You have seen laser pointers made out of it. If not gallium arsenide exactly, alloyed form of gallium arsenide, you've seen lasers out of it. You've seen LEDs made out of gallium arsenide. Those are the common, that means gallium arsenide is an optoelectronic material. So question is why silicon is not an optoelectronic material, gallium arsenide is an optoelectronic material. These kind of properties we are going to be able to decide from band diagram, and hence we had been studying it. But with these few names which I have written down here of semiconductors, there are many semiconductors around. In fact, there's huge, maybe hundreds of them literally, which are around, of which practically maybe 5, 10, 15 are at least used semiconductors. Let's start looking at their crystal structures. So what we're going to do is first look at the crystal structure. All these two semiconductors crystallize in form of what is called as diamond cubic structure. As the name suggests, that obviously it's a cubic, but if you recall, if you look at those 14 Bravais lattices which I had mentioned earlier first part of the in the first module, you'll recall there was nothing called diamond cubic. There was simple cubic, there was face-centered cubic, there was body-centered cubic, but nothing called diamond cubic structure. Those were lattices. On those lattices, if we put atoms, then they form crystal structure. So if we put crystal atoms in a certain way, then the structure that emerges, we start calling it as diamond cubic structure because it resembles a structure of diamond. And therefore, but remember, it is not a lattice. There is an underlying lattice. Underlying lattice in all these materials is FCC. While we are at it, let's look at gallium arsenide also. Now there are two types of atom, gallium and arsenic. This crystallizes in what is called a zinc blende structure. which mimics in structure very close to what is a diamond cubic structure. So using some 3D models and also some pictures, let me try to explain what these structures are, what these materials are. Let's do so. Here is a example of diamond cubic structure. So if you look at this, here is a diamond cubic structure which I am showing you. Let me show you a 3D model. Let me pick it up. Here in my hand is also a same structure, diamond cubic structure. You notice, first of all, the atoms on the FCC side. As it says, lattice is FCC. So let me mark the FCC positions. Here is a FCC position. Here is a FCC position. Here is a FCC position. These are the cubic positions. These 8 of these are the FCC positions of the cubic corners. Then on top of that, the face centers right here, right here, right here, right here, and one more, 2 more right here, and one in the back right here, this one. Now you see, in addition to that, I have 4 more atoms in there. Which ones? Those 4 atoms are right here, 1, 2, 3, and another one here, 4. Let me show you in this model. Notice here is FCC lattice. This FCC lattice, if you look at, then you will see it as this, these corner positions, this, and this, the corner positions. Then the face center position right here, right here, right here, right here, and right here in back. But then there are 4 more atoms in there, which are right here. These are the 2 atoms in the inside. These are the 2 atoms right here, and there are 2 more atoms like this. 2 atoms, one here and 1 atom right here. These are the 2 atoms which are inside this cube. These 4 atoms. So there are a total of 8 atoms in there. 4 from FCC, 4 from FCC, and 4 that I'm showing you inside. Meaning thereby, if you think of this structure as 2 interpenetrating FCC lattices, imagine like this. Imagine a FCC lattice in which you have kept atoms on the, where you kept the atoms on the FCC positions, and then take another FCC lattice, take a similar cube, and then shift it. Let me show you. Maybe let's show it like this. Suppose this we take as origin, and let's think of this as x direction. Right here as the x direction, right here as the y direction, and let's think of this as the z direction. If I take this as a cube and this as the origin, and I take another FCC lattice where atoms are on the lattice positions only, that is at wherever the lattice position is, FCC lattice position, we keep the atoms there. Then what we do is we take another FCC lattice with atoms on the FCC points. I take another cube and place it. We move quarter, 1/4 in this direction, x direction, 1/4 in y direction, and 1/4 in z direction. And I locate this lattice point. So this point moves right here, and if it so moves, then imagine all the other lattice points also moving. And if all the other lattice points, if you start looking at, so I get an atomic position here. This particular atom, which is the face center atom, would have moved up here. This particular atom, which was at the bottom of the face center, would have moved right here. And this particular atom, which was at the face center on this side, would have moved up here as I move quarter, quarter, quarter. And all other FCC atoms would have gone out of this cube, So they will not be part of this cube. So if I confine my picture on this cube only, then I will generate what? I will have my original FCC atoms plus these 4 atoms which I just showed you as the atoms at this center, at the origin, and I move quarter, 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 I move here, and this at face center atom, this face center atom, and this face center atom give rise to another 3 atomic positions. So that's what our diamond cubic structure is. That's what the structure of silicon is. So here's the structure of diamond, here's the structure of silicon, here's the structure of germanium as well. So they all are diamond cubic structure. So that's what I have described to you. Now let's go back to the paper. I'll keep this down, and we'll look at the one on the screen itself, on the paper itself. So now if I look at the next page, let's look at some of them. Then what do you see? Maybe go back and see, look at the nature of bonding. The bonding is tetragonal. This is the atom from corner origin. From origin it had moved out here, it had moved to this position, new atom was at quarter. This particular atom, if you notice, is bonded to what? It is bonded to this corner atom. There is a tetrahedral bonding. It is bonded to this atom, it is bonded to this particular face center atom, is bonded to this face center atom on the base, and it is bonded to this particular face center which is on the back, on the face, towards the screen. So these are four. You can see that each atom is tetrahedrally bonded. So silicon material, essentially each silicon atom is covalently bonded to other silicon atoms, and the nature of bonding is these tetrahedras are forming using this, and this. We start forming a tetrahedra. Then we can form a tetrahedron based on, so notice that what happens, that this is the face center, this is the corner atom, this is the face center, face which is towards me here, and there is a face center. These form a tetrahedron, and in between this tetrahedron sits this particular atom which you see here, this particular one, which is the tetrahedral center of the tetrahedra. That's the silicon atom, and it's bonded to these four smaller ones which I'm showing you here. That's the nature of bonding in silicon. So that's what we call as diamond cubic structure, and silicon is totally covalently bonded in these. Also, if you wish, we can similarly describe the gallium arsenide structure also. In this gallium arsenide structure, now notice, now we have two types of atom, one gallium and one arsenic. You can think of in same way, like I said, two FCC lattices, one FCC lattice, one FCC cube, and then take another FCC cube and shift it by 1 4 1 4 1 4, and you get what is called as diamond cubic structure. So you can do the same thing for gallium arsenide, and then the structure is called zinc blend structure. Namely, you take a FCC of gallium, that means take a FCC lattice, on the lattice points put gallium, similarly take another FCC lattice, on the lattice points put arsenic atoms, and then you have these two FCC structures displaced from each other by a quarter, just like in diamond cubic structure. And what you would get then is essentially a diamond cubic structure, what is called as zinc blend structure. Essentially it is same, atomic positions are same like diamond cubic structures, except now there are two kinds of atoms involved, meaning thereby you can think of it as follows. You can think of these as, let us say, red ones as, if you wish to think of arsenic, you think of then green ones as gallium in this case. So arsenic, now you think on FCC positions of this particular cube which is shown in this picture. There is a FCC cube here, so you think on FCC side there is the arsenic sitting, and then you think of the gallium sitting, the green atoms, the gallium ones, those are the inside four atoms right here, this, and this are the inside four atoms which you also saw in diamond cubic structure. You think of those as gallium. Conversely, equivalent way of thinking would be, if you interchange, if you think of this as gallium, this particular red ones as gallium, then you start thinking of green ones as arsenic. Structure remains the same anyways, because there are two interpenetrating FCC lattices, so it does not matter which FCC lattice you look at, FCC cube you look at, the one for arsenic or one for gallium. Either way, whichever you look at, it's the same structure you're going to get. So that's a gallium arsenide structure, and that's called the zinc blend structure. So this is the nature. You can again see in gallium arsenide is also covalent bonding going on. There's blue markers here showing the covalent bonding. The bonding is by and large in gallium arsenide also covalent bonding, except that now arsenic is more electronegative than gallium. As a result, there is a partly ionic electron cloud shifts, and as a consequence, there is a partly ionic character to gallium arsenide, whereas silicon and germanium are purely covalent. Gallium arsenide is also largely covalent, but about 32% of bonding character is ionic bonding. 32%, and rest is all covalent bonding. So that's the nature of bonding in some of these semiconductors, and also and all these semiconductors essentially show similar bonding, though some of them are ionic semiconductors as well. But the ones which we will be talking about are predominantly covalent and partly with some ionic character in them. All right, with that, let's go back to our screen here, which we were talking about. In so FCC, I've shown you in FCC, both are FCC lattice with atoms at 0, 0, 0 position, and at atom at 1/4, 1/4, and 1/4 position. If both are silicon at both these positions in FCC lattice, they are both as silicon or germanium, that's diamond cubic structure. If one of them is gallium, other one is arsenic, then it is zinc blend structure. Having done this, now let's go to band structures of semiconductors. Here it is. So this is all we've been waiting for. Now remember, this I've shown you that how these band diagrams are plotted. Now in this case, therefore, you understand the k axis. Here is the k axis. I'm looking at silicon. This is the silicon semiconductor, and you look at the k axis. Remember, here's the gamma point. The center point k equal to 0 corresponds to k equal to small k equal to 0. That's what it corresponds to, this gamma point, the center of the Brillouin zone. And then you start moving in some major directions. In this case, now these energies are more realistic energies. Energies are estimated by, we have done free electron theory, which does not give a band gap. Then we have done nearly free electron theory, a one-dimensional theory, to show how periodic potential can give band gap. Then we said that calculations are fairly complicated, so we're going to use these, somebody has done the calculation, and we'll use those calculations to show the realistic band diagrams, and this is what they are. They are here for silicon, germanium, gallium arsenide, cadmium telluride, gallium phosphide. So using these band diagrams, now we're going to try to interpret as to what they're good for. So in order to do so, let's start looking at one of them and slowly build up similarities and differences between these band diagrams. That's how we're going to look at it. So if you notice that, first let's define some of the directions. Two important directions I'm going to define is this going from gamma to x and gamma to L. These are the two directions. You will recall, let's just look at it. Let's look at this. Recall, this is the Brillouin zone. This is the Brillouin zone we have been talking about. So what is the gamma point is right here. Gamma to L. Gamma to L direction is what direction? Then you can clearly see it's a 1, 1, 1 type of direction. Gamma to L. And what is gamma to x type of direction? Gamma to x type of direction is 1, 0, 0 type direction. Gamma to x, and this is gamma to L. This is the direction with gamma to x and gamma to L. So 1, 1, 1 and 1, 0, 0 type of direction. So let's go back. So gamma to x, as we say, is 1, 0, 0 direction, and this is 1, 1, 1 direction as we go from gamma to L. What do you notice? You notice that all these energies from here to here are allowed energies in silicon. Then you notice there is an energy state at some k value. At some k value, energy is allowed for electron. So therefore, and what do you notice? In between, there's this energy which is not allowed. Hence, this is the band gap. So this is what we call as band gap, of course. So what you notice, here is a maxima in this lower band. So there is one band, here is a band, and here is a band. These are allowed energies. This is a band and there is another band. This is the top of the band. Right here is the top of the band. Right here is the top of the band, which is same as this point. Since both are gamma point, this is also gamma and this is also gamma. Therefore, both are same energy. So you can see this is the top of the band, and then you see the other one, the higher one, has lowest energies right here. In between these two states, therefore, is what is called as band gap. So we see a band gap, and indeed, therefore, it is semiconductor. The value for this is about 1.1 eV. So Eg is about 1.17. Depends on what temperature you want to talk about. All these calculations, by the way, done at 0K. Though we freely apply them at higher temperatures, at room temperatures also. In all these semiconductors, you will find that energies are, in all these semiconductors, as I go through, the energy gap, the band gap will be about 1 to 3 electron volt. You ought to get a sense of what this means, 1 to 3 electron volts. Visible energy range is somewhere from 4000 nanometers to from 400 nanometers to about 800 nanometers is a visible range, and that range corresponds to somewhere energy of about 1.5 or 1.5 to about 3 eV. So 1.5 to 3 eV is about our visible range. What else? At room temperature, if I look at KT, then it is about 29 or 30 milli-electron volts. So that's 30 milli-electron volts is what this KT energy is. So notice that when you talk about 1 to 3 eV and you talk of room temperature, then this 29 milli-electron volts is sufficient enough to cause some electrons to jump this band gap. If band gap is greater than this, then you will find that there will be hardly any electrons able to jump from lower energy state to higher energy state. Anyway, that part we will do later, but keep this in mind that KT energy is about 29 MeV and the silicon band gap is about 1.1 EV at room temperature. At 0K it is slightly higher, it's about 1.17 EV or so, 1.17 electron volts. Now, if we start putting electrons in silicon, we find that electrons fill up to this energy. Up to this energy, the electrons are completely, up to this energy, electrons completely fill up. When electrons fill up to this energy, and then all this energy, higher energy levels which you see here are empty. That means what we start calling the lower band as the valence band, which is completely full of electrons, and we start calling the higher band which is completely empty as the therefore conduction band. As the name you will see will make sense as we start doing some carrier statistics also eventually. But the point is, at 0K, conduction band in silicon is completely empty and valence band is completely filled. Now, having learnt in the previous lecture, you recall that a band which is completely full cannot conduct, a band which is completely empty cannot conduct, which means cannot contribute to conduction. What does that mean? That means silicon at 0K will therefore be an insulator. It won't be able to conduct at all because the bands are completely full or bands are completely empty. Now, you start looking at other semiconductors also, germanium. You look at germanium, notice the nature of the band at gamma point. This maximum in the band or the valence band always occurs, and in all these semiconductors we find just what you find that whatever the maxima is right here, in all these 5 different materials I am showing you, where the maxima is, maxima occurs at gamma point. Maxima in all these cases occurs at gamma point, you would notice in all these cases, and electrons fill up to this energy level. In all cases, therefore, we call these energy levels, these bands here to here to here, as the valence band. All these are valence band, and across from here to here, in all these cases, therefore, are conduction band. If I look at germanium, this energy Eg is only 0.67 electron volts at room temperature, about 0.74 electron volts at 0 Kelvin. In gallium arsenide, this energy is about 1.43 electron volts. This band gap is 1.43 electron volts, which is Eg room temperature. Remember, this is a room temperature. All these are room temperature, about 1.5 or so at 0 Kelvin. And then cadmium telluride, this energy gap is 1.49 eV, and in case of gallium phosphide, this is equal to 2.26 eV. This band gap is equal to 2.26 eV. What I was trying to first point out to you was that in all these semiconductors we are noticing that valence band maxima or the lower bands maxima occurs at gamma equal to 0. That's the first point I'm noticing in all these band diagrams. So let's just look at that a little bit in greater detail. So we find, let's start looking at, so first point I want to make is maxima and indeed all these are showing a maxima, not minima. All these are showing a maxima. So there is a maximum which is showing up, not a minimum showing up, whereas in conduction band if you look at, all those showing a minimum, not a maximum. There is a minimum here which we are talking about, where minimum we are talking about, not a maximum. Whereas in case of valence band, we are always showing a maximum. So we are going to talk about now valence band. I'll abbreviate this as VB from now on. So maxima occurs at gamma equal to 0. At gamma point, which means K equal to 0. That means K equal to 0, that means the center of the Brillouin zone. Always the maxima in energy is occurring at this point. If I start looking at some detailed structure near the valence band, then it looks like this. If I now plot like this, this is gamma point and this direction is, let us say in this direction I am plotting 100 on the right hand side and 111 on the left hand side, left gamma to L and gamma to X. So let's do that. So this is 111 direction and this is 100 direction. If I plot this energy, clearly you see that there is a maximum in this. But if I expand this view, then we find that this structure is more complicated than that. In fact, we see that something like this in case of germanium. Similarly, and this is energy, of course I am plotting. This is basically, this is a expanded view of the picture here, I am plotting an expanded view. In other words, you can see between this and this, I am showing a gap when I am plotting an expanded view, whereas at this scale you are not seeing that. So if I look at that, then there is a gap in there, and if I plot the same thing for gamma point for silicon in 100 and 100 direction and 111 direction, then we find that there is a band like this and there is a band like this. Band like this and band like this, and this I am going to name as split off band. And this actually is two degenerate bands. What does that mean? That means there are two bands overlapping on each other. In energy, therefore, they are degenerate. What is the consequence of it? In a minute we will see. Well, not consequence right now, we will just show a character right now. We are just pointing out differences between them, finer differences between them, and they can be useful. They have been used, they will be used in some context. Some we will use and some we will not use, but knowledge of it will help you. And in this case, in case of gallium arsenide, this looks something like this. Essentially what you see in all these three cases, let's just take a look at quickly here. In all these cases, I am showing you here, 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 here and here, here and here. These I am showing you, but I am showing you a detailed structure now. In all these cases, we are finding that there are two bands right at the top, right here. These are the two bands. In this case, we are going to call it heavy hole, and this is a light hole, and of course then split off. Here's the split off band right here, split off band. What do you see? Then each of these valence band where the maxima occurs at gamma point, you find that these, in case of germanium and in case of gallium arsenide, at expanded view, we can clearly see separated from the maxima, the split off band, and hence the name split off band. In case of silicon, this split off only 0.044 electron volts below the two degenerate bands, and hence they seem touching each other because the energy gap is so small, whereas in case of gallium arsenide and germanium is slightly more, and hence you can clearly see them. Whereas if I go back to full scale picture where these energies are scale, you can scale this energy now. You can see that if this is 1.43, then what all the other energies will be, what the scale of energy will be. At this scale, then this split off band cannot be seen as a separated out. Okay, then what else you see? What else you see is that all of them have a degeneracy at gamma equal to 0. At gamma equal to 0, essentially there are two bands overlying on each other, whereas little far apart, in case of germanium, in case of silicon, they are pretty much lying one on top of each other, and therefore we are calling it degenerate band. Not only at gamma point, but through and through around that area, near the gamma area. In case of germanium, also they are nearly on top of each other, except in this region right here where they start splitting off. In gallium arsenide, we find that this splitting, the curvature itself at gamma equal to 0 is different of these two. Now recall, what do we mean by? Recall that nature of this, since all these valence bands have this nature where they are concave downwards, and recall yesterday we said concave downward surfaces means they are hole-like surfaces. Holes like to live there on top of the valence band. Therefore, since electrons will roll down and live in the lower energy state, of course when they're completely full, electrons come all the way up to top. So if some electron has to go to higher energy, it's simply the topmost electron goes and jumps. And what does it leave behind? It leaves behind hole right at the top of the valence band. Effectively, we can think of that holes reside on the top of the valence band because all the electrons would have taken the lower energy states. Therefore, we can think of, and therefore such surfaces are called, where concave downwards, are called hole-like surfaces. And once they're called hole-like surfaces, then you can think of the effective mass of hole also. Remember, the curvature is more, that means effective mass will be smaller. And if curvature is large, then in that case inverse of that will be the effective mass, and therefore it will be light. So you can see the one which has a greater curvature, the one here is a greater curvature in this curvature, whereas this has a lower curvature. Since it has a lower curvature, therefore inverse of that would have, and therefore hole residing on that band would have higher effective mass than the one which is on this curve, and this is why we call this as heavy hole band, and this is the light hole band. So this is the differentiation between all these. Okay, so these are the similarities we see and differences, similarities and differences we see in valence band. Now let's look at conduction band. Now let's start looking at the conduction band. What do we see? And we'll abbreviate from now on as CB. Conduction band, again we go back here. Now something interesting things happen in this. Now conduction band has a minima. First of all, in all these cases you see there is a minima. Right here is a minima. Right here is a minima. Right here is a minima. All these have a minimum. That means when electrons go, they concave upwards. So that means they are electron-like surfaces. Electrons will jump and live at the lowest bottom of it, and therefore they are electron-like surfaces. And therefore we will talk of effective mass of electrons at these points. Now where does the minimum occur is a very, very important question. We have noticed for valence band, the maximum always occurs at gamma points. But in case of conduction band, all these materials have a different, there are differences. If we look at, for example, silicon, the most common one, we find that minimum occurs near to the X point, X is here, minimum occurs somewhere here. This point, maybe you change the color of the pen, right here is where the minimum occurs. This minimum occurs as we go from gamma to X at about 0.8x. So this point where the minimum occurs is about 0.8x is where this minimum in conduction band is occurring. Now you can see that 100 direction this should represent 6 equivalent directions. 100 direction means, what does 100 mean? 100 mean in x direction, in minus x direction, in y direction, in minus y direction, in z direction, and minus z direction. So there are 6 equivalent 100 type of directions. So this minimum which you see in silicon really represents 6 equivalent minimas and occurring at x at slightly 0.8x as you go from gamma to x. At 0.8x is where the minimum in energy of the conduction band occurs. The important point is that minimum of the conduction band occurs at a different point than minimum of conduction band occurs at a point, means in k point, on k space, a point other than valence band maxima, which is always at gamma point, Such semiconductors are called indirect semiconductor. Such semiconductors are called indirect semiconductors. Alright, if we look at germanium for example, then we know that this maximum occurs about 0.74 electron volts at 0K and about 0.67 electron volts at room temperature. Where does the minimum occur? Sorry, I shouldn't have plotted here. So where does the minimum occur? Minimum occurs not here, but it occurs right here. Right here is the minimum. Maximum is right here, and the minimum energy which is on the higher band is right here where I am showing the red point. So what does that mean? That it occurs at L point, at the edge of the Brillouin zone. So at L point in 111 direction as you go, then if you go in 111 direction, then at L point the minimum of the conduction band occurs in germanium. Of course, how many directions are there? There are 8 111 directions. So you think of diagonal, body diagonal of the cube. So how many directions are there? So you can think of plus direction and a minus direction. So therefore you can think of 8 such directions. But because it occurs at the Brillouin zone boundary, therefore since there are 2 Brillouin zones, since it's a boundary, it's shared between 2 Brillouin zones, we will therefore think of this as 4 equivalent minimas instead of 8 equivalent minimas, which you see here. So this is a idea of degeneracy as to how many minimums are there. So this is conduction band in germanium occurs at, so what would the semiconductor be? A direct band gap semiconductor or indirect, I should say indirect band gap semiconductor. So there will be indirect or direct band gap semiconductor. Clearly this would also be indirect band gap semiconductor because the minimum occurs at L point, whereas the maximum of valence band occurs at gamma point. Now see striking difference in case of gallium arsenide. Where does the minimum occur? The minimum in conduction band minima is at same gamma point, same as where the maxima of conduction band is. So therefore this is a important difference, and such a semiconductor, since it occurs at same K point, we call it direct band gap semiconductor. So that's a direct band gap semiconductor right here, which we see is gallium arsenide. Okay, so if so, now let me point out to you, I already mentioned to you that silicon and germanium are not optoelectronic materials. Gallium arsenide, I said, is an optoelectronic material. You have seen LEDs and lasers is what I mentioned. I hope this begins to give you a clue why, or it tells you that there must be something, what I'm telling you must be somewhere related to it, that silicon and germanium, not being indirect band gap semiconductors, are not good optoelectronic materials. something which has a direct band gap is an optoelectronic material. Now you can hopefully begin to see why we have been doing, why I've been trying to so hard to understand how band diagrams are to be read. Okay, let's just move forward a little bit further and see, look at cadmium telluride, which has a band gap of 1.49, and notice in this case also the minimum occurs at same point as where the valence band maximum is, at the gamma point itself is the, and also remember the band gap is 1.49. Really this is the edge of infrared, and so clearly this could possibly, if I work with my linkage, though I have not shown you how, but if we work with this linkage that the direct band gap semiconductors will be optoelectronic materials, then you can see cadmium telluride, which has a band gap of 1.49, is just reaching the IR range, infrared range. You can see it's the lower end, it's the lower end, is near the red end. So further lower energy means infrared energies. And if you think of cadmium, mercury telluride, etc., then the band gap becomes even less and truly in IR range. If you recall, or if not recall, rather, if you think of what kind of materials you would make your night vision goggles, etc., then I hope you can begin to see what kind of information these band diagrams can give. If they are optoelectronic materials in IR range, and if IR is what you sense in night vision, then these materials may be a choice. Okay. Then another material which is quite important material these days, especially we're finding it to gaining importance, is gallium phosphide. In this case, of course, so this is of course clearly direct band gap. So this cadmium telluride right here, and then in gallium phosphide, this minimum occurs right here, not at the gamma point, and therefore this is an indirect band gap semiconductor, though on account of different colors of LEDs, gallium phosphide does get used a little bit. But gallium phosphide by itself, by including it in gallium arsenide, with gallium arsenide, you could retain largely direct band gap connector. That means if you alloy gallium phosphide and gallium arsenide and possibly retain the structure of gallium arsenide, then you could use it as a direct band gap semiconductor, but by itself it is not an optoelectronic material. Alright, so this is the background. Now let me reduce this whole problem therefore to as follows. Let me reduce this whole problem to two categories. One more point I want to make for gallium arsenide. One more point let me make for gallium arsenide. There is a minimum, of course I told you, at gamma point itself, but where is the next higher minimum? If you look at the next higher minimum occurs right here. This is the next higher minimum at the L point, and the difference between these two energies is only 0.29 electron volts. That's the difference at the L value, what is called as L valley and gamma valley. Here's the gamma valley, the minimum, and here's the L valley, the minimum at the L point. And the L point minimum is only 0.29 electron volts higher. So if sufficient electric fields exist in a device, if we make a device with gallium arsenide, sufficient electric field exists, then remember electric field application means changing the K states. So if you have sufficient electric field, it is possible that you could populate some of the electrons in this L valley. If you populate in the electrons in L valley, what do you notice? You notice that what is the curvature of it? Its curvature is at L point. The curvature at L point is less than curvature at the gamma point. At the gamma point, the curvature is more. So what about the effective mass? Wherever curvature is less, inverse of that is the effective mass. Then in that case, effective mass at L point of effective mass of electron at L point will be higher than effective mass of electron in the gamma valley. So if I now apply electric field and populate some electrons into the L valley, if I do so, what will happen? These electrons which had a lower effective mass at gamma valley, when they move to L valley, they start having higher effective mass. Strange. Now such phenomena can give rise to negative differential resistance. Interesting devices can be made, and that you can interpret from the band diagram, because effective mass from being, imagine something is moving and suddenly as it moves somewhere, it becomes heavy. Suddenly it becomes heavy, which means its velocity will decrease now. If velocity will decrease, if so happens, then what does it mean? It means you have negative. So what happens? What its consequence on that will have a consequence in the current. So what would you see? You would see negative differential resistance in this case, and you indeed can make such devices with gallium arsenide. So that's the important facts I'm trying to point out, some tidbits I'm trying to tell you because of the information kind of information you can get from the same electron dynamics we did and this direct indirect business on which I'm further expanding on about optoelectronics. Based on all these things, you can get a lot of based on these things you can get a lot of information from these band diagrams, and you can select materials appropriately therefore. So let's further continue on to this idea. Let's reduce our band diagrams to two categories schematically. In one case we plot it as follows, where we always show a valence band. So here's a K, here's a K, and we will show always valence band like this. We may show these two curves, or we may show only one, does not matter. But in one case I will show a minimum elsewhere from gamma point. So this is the gamma point, this is the gamma point, and this is the energy. This is the energy, and I'll show a minimum here, somewhere here, and a minimum here. So this is really the band gap. This is really the band gap we are talking about, and such a band gap minimum occurs at different K point than here. So this is an indirect band gap semiconductor. Band gap semiconductor, indirect band gap semiconductor. Conversely, we can plot a direct band gap semiconductor same way. Here is the valence band I am showing, here is the valence band, and conduction band minima occurs here and then here. So the minimum occurs at the same K state. Now you can see if an electron sitting here, if an electron sitting right here has to jump, has to go here, if it has to move like this, then it can do so by making changes in energy, and this is delta E energy, and by making changes in delta K. The K must also change and E must also change. In this case, of course, in this case all you require is delta E, change in electron going from here to here. Electron going from here to here would imply that a change in delta E only, no change in delta K. If I look at these two semiconductors therefore, and I start looking at the absorption profiles of these, so what I'm going to do, I'm going to do experiment like this. I'm going to do experiment in which I'll take a semiconductor, I'll shine light of various wavelengths onto this, and this and I will monitor what intensity is transmitted out of this, and this I will do at various wavelengths. If this is thickness x, then we say I as being equal to I0 e to power minus some absorption coefficient x, and I am going to do this experiment for different wavelengths. So what I am going to then plot is, I am going to define this alpha quantity as equal to, then I am going to define as minus 1 over x times log of, let's use different symbol, not x, x doesn't look nice, so let's use t, thickness. Let's use thickness t, and t log of I by I0, or I can plot it 1 by t log of I0 by I. So this is what we are going to define as absorption coefficient alpha. So I am going to now show you, if I have done the experiment like this, I measure I and I naught for different wavelengths, and I therefore extract what the value of alpha is, and then I am now about to plot value of alpha at different wavelengths, that means absorption coefficient at different wavelengths for different semiconductors. So if I plot that, let me show you a plot of it. This plot looks something like this. Here's alpha on a log scale. I am not drawing this scale, and here is energy. So at different wavelengths or different energy I am going to do. So this is electron volts energy, this is 0.6. I am putting this also at this is, here is 1, here is 1, here is 2, here is, let's say, 3, etc., etc., etc. All right. Now if I look at this, what do I find? I find in case of I find a line something like this. So let me draw a line like this first. I'll show you some. A different color line. Then I'll show you another different color line. So somewhere here. This for germanium, this for gallium arsenide, or this for gallium arsenide, and this for silicon. What do we notice? We find that I have if an indirect bandgap semiconductor, then I have something like this. And if I have a direct bandgap semiconductor, then I have something like this. K versus E. In case of silicon, as I shine light, clearly as long as energies are less than this, which is 1.1 eV or so, I cannot have any absorption. I don't have sufficient energy to promote the electron from here to here. But when I get, so therefore for all values up to 1.1, I do not get absorption, hardly any absorption. But when I get to 1.1, I get some absorption. As the photon energy continues to increase, then it becomes possible for this kind of directly to the higher bands also. It is possible to absorb into this also, and then I get a steep absorption one more time. Same thing happens in germanium. First absorption occurs where the band gap is about 0.66 electron volts. Up to here, a weak absorption. But when I can absorb into the higher energy range directly, then I get a sharp absorption. Whereas in case of gallium arsenide, which is a direct band gap semiconductor, notice that this gap being about 1.5 or 1.43 electron volts at room temperature and about 1.5 at near 0 K, this absorption is immense, right away. It's an immense absorption straight away. There's a huge amount of absorption going on in gallium arsenide. That is because you can now absorb electron right from here. All you need is a photon energy, and it simply jumps here. This is a two-particle event, namely electron interacting with the photon, and it gets excited into this new state, the higher energy state, which is in the conduction band. Whereas in case of silicon and germanium, when the photon of 1.1 electron volt in case of silicon comes, by energy it is possible for this electron to jump. Let me draw this picture one more time. So in a different way, something like this. Here is 1.1 electron volts in case of silicon. It is possible for this electron to jump up to here, which is 1.1 eV for electron jump here, but there is no state. There is no state here, so electron cannot live here. In addition to that, therefore, it must change its K value also. Something must be provided. So photon and electron alone are not sufficient enough. There must be something else added on which allows this delta K also. The K comes from phonons. Quantized lattice vibrations. Phonons must be involved. This is quantized lattice vibrations. Phonons don't carry much energy. Phonons, the lattice vibrations have very small energy. Remember, you use IR to detect them. So phonons have very little energy, but they have large crystal momentum. Whereas photons have very little momentum in them, crystal momentum in them, but they have large amount of energy. So a photon transition, when I show in gallium arsenide, I show a vertical transition. That means if an electron comes and excites this electron, then the energy changes by 1.5 eV or 1.43 eV or so. eV in case of gallium arsenide, by this much amount in gallium arsenide, it changes, the energy changes, but there is no change in K because the photon which came had no no crystal momentum. It could not change the crystal momentum. K value did not change, so I show it as a vertical transition. Whereas in the case of silicon and germanium, it is required for me to change delta K also, and for this electron to go this much by 1.1. So a photon of 1.1 eV comes, it has no crystal momentum, so all it can cause is a jump like this, vertical jump up. When it goes to vertical up jump, there is no state. Simultaneously, third particle must also come in, which is the phonon, which should provide the crystal momentum, and then only this electron can come here. Point is that it is a 3-particle event: electron, photon, and a phonon. Probability of that happening is much lesser. So therefore, absorption in case of silicon and germanium at 1.1 eV, and or in case of germanium at 1.66 eV is very weak, and we get very weak absorption right here at those points. Very little absorption because you require phonon also. But when photon energy increases, then transition from here to here becomes possible. You have sufficient energy, photon has sufficient energy, so these jumps become possible. These jumps becoming possible means that now I don't need phonon. Now it becomes a 2-particle event, because this is jump, vertical jump only, no change in K states, and therefore you get a large increase in absorption when that happens, when this energy becomes equal to the next higher level at gamma equal to 0 itself, at gamma point itself, at K equal to 0 itself, then this absorption occurs very rapidly. Clearly now you can begin to see that optical materials will be there, those which have good absorption, and hence they must have direct band gap. With that thought, let me close this right now, and then we'll come back to this opto part again one more time after doing some carrier statistics.